like to welcome you again about to our webinar about homogenization and shaping of LED light by micro-optical components. My name is Hagen Schweitzer. I'm Chief Sales Officer of Light Trends. And I like to explain in the following hour how you can shape and how you can shape LED light, including partial coherence, diffraction, interference effects, and polarization. The following micro-optical components that I will introduce can be used for monochromatic light or white light. LED, you will see that some elements are quite sensitive, for example, for white light. Other elements are not so sensitive for white light. I will explain the following optical components. These are computer-generated holograms, faceplates, diffractive diffuser elements, microlens arrays, grating cell arrays, prism cell arrays, and mirror cells arrays. These elements can be used for the generation of almost arbitrary 2D light patterns. And I will show you also very short how you can export resulting surface profiles in different file formats for the fabrication process. I like to mention that we offer in March next year 2 trainings for Virtual Lab. Here in this webinar I can give you just a short overview of the different homogenization concepts. But if you like to learn how to run and design or simulation with Virtual Lab, then I recommend our training from March 19 to 20. It is called Analysis and Design of Light Shaping and Homogenization Systems. It explains within these 2 days how the design and simulation concepts in Virtual Lab work. This training expects that you have some elementary skills in Virtual Lab, that you can set up a light path diagram or a lens system. If you have no knowledge of Virtual Lab, I recommend to join also the first part of the training from March 16 to 18. It gives an introduction into Virtual Lab, into the setup of laser systems, into parametric optimizations of laser systems. So that are the basics, so that you can work quite good with Virtual Lab in the second part. The training location is Jena in Germany. I like to give some comments concerning the webinar software that you used. It's called GoToWebinar, and you should see a window like this. And if you should have a question, you have 2 options to ask me questions. There is here this raise hand button. If you click this button, I will see this, and I can unmute your microphone. Or actually, the best option is, and I see already one of the participants used this option. It is this question window. So if you have a question, just send me a short message. I can read this and answer this question. And here I got already one question. Mr. Dannenberg asked if every one of you can have the slides of the webinar. Yeah, and I will record this webinar. So we will upload this webinar to our webpage, but also to our YouTube channel, so you can see this webinar again. But in addition, we will also upload the slides of the webinar. You will also see that I will use some samples which are available on our webpage. And every sample has a specific number. And if you go to the download area of our webpage and enter this number, you will find the sample and you can download it. So the webinar video, the slides, and also the sample files are available. And if you don't have a trial version of Virtual Lab, just go to our webpage and register for a trial version, and we will send you a link for the download of the trial version together with some tutorials and sample files. So now let's start. I like to start with a short introduction into Virtual Lab. So if you are not used to work with Virtual Lab. If you don't know Virtual Lab very good, then I like to give you a short introduction. What is the basic concept, the basic idea, and after this introduction I will start with the homogenization of LED light. So if you need to analyze and optimize modern optical systems, you have often to handle a lot of different light sources, for example coherent laser beams, but also partial coherent sources, for example LEDs or multimode laser with specific temporal partial coherence properties or spatial partially coherence properties. But you need probably also to simulate ultra-short pulses, you need to simulate amplitude, phase, polarization and so on. Another important point is, and you will see this also in this webinar, if we model optical systems, for example, for homogenization of LED light, then we have typically a lot of different types of optical components. We can have some lenses, we have microstructures, diffractive optical elements, maybe also some nanostructures. So we can say we need to simulate different components with structures, with features from nanometer or micrometer to meter scale. So it's very important that we can simulate all of these components in a single optics software. And finally, we need to evaluate the quality, the optical performance of our optical system. And that means we need to evaluate merit functions, we need to model the effect of the light in our application. And these need access to amplitude, phase, polarization information, to energies, at energy densities, maybe pulse lengths, polarization, and so on. And the question is now, how can we handle this? And we have here actually, if you see different types of optics software, then you will see that we have typically two different approaches. There is ray tracing software, a software that is based on ray tracing, and there are other software tools based on physical optics. So what does it mean? So if we use ray tracing software, we use typically ray bundles to model light in a computer simulation, and it means rays carry at least position and directions informations. Sometimes we have also a little bit more information like power or like polarization. This depends a little bit on the ray tracing software. If we work with physical optics modeling, then we use an electromagnetic field presentation. And electromagnetic fields can carry always all information of a light distribution. And, okay, I got here the message that somebody cannot hear me. Can other participants hear me? Okay, because I got here actually the message from GoToWebinar that the audio should be okay. Okay, so that seems to be just a problem of one of the participants. Okay, so I will continue the webinar, and if you should have some trouble with the connections, we will upload the webinar, as I mentioned, to our YouTube channel, and you can just watch the video to any later time. Okay, in physical optics software we use an electromagnetic field representation, and this means that we can store all light information in the computer. We can store amplitude, phase, polarization, coherent light, incoherent light, partially coherent light. We can store ultra-short pulses, for example, and color in the computer. So we are always able to model all properties of our light source, light distribution. Yeah, it's maybe sometimes difficult to measure all properties, but if we know it, we can store it in the computer. So, and in Virtual Lab, we have something that is called, we use a simulation concept that we call unified field tracing. So we have actually in Virtual Lab also a ray tracing propagation that is based on geometrical optics, but unified field tracing is more flexible because we propagate fields through an optical system. And in unified field tracing, we are still able to use geometrical optics to propagate rays that carry the full field information to an optical system. But if it turns out that we have, for example, diffraction interference effects, we are able to use rigorous solutions of the Maxwell equations for the light propagation, or to use an approximate physical optics propagation model that includes already diffraction effects, but that is probably not so time and memory consuming like a rigorous solution. So what does it mean for an optical system? Let's assume we have a system with lenses, freeform surfaces, DOEs, index modulations, and now VirtualLab is able to use in every region of the optical system and different modeling techniques. So in different physical optics model, let's say an optical model from geometrical optics to rigorous can be used for the simulation of the light propagation. And it is typically not a good idea to use the most accurate propagation model. We should always select a propagation method model that is sufficient accurate from a physical point of view, but also as fast as possible. So VirtualLab can simulate a lot of different optical components. Sure, we can simulate light propagation in free spaces. We can propagate light through lenses, but we can also simulate, for example, prisms, lens arrays, gratings, DOEs, diffusers, and so on. And for every type of optical component, we have typically a lot of different propagation models available. So from geometrical optics, we have for several components also rigorous solutions, but not for every component and rigorous solution is available, because sometimes it is just too time and memory consuming and probably also not required. So for every component or type of component, different models are available depending on the physical accuracy and also depending on the amount of calculation time and RAM memory that we are able to use. So in this full field tracing, this unified field tracing concept is included in 5 toolboxes. These are starter toolbox, diffractive optics toolbox, grating toolbox, lighting toolbox, and laser resonator toolbox. And in this webinar, I will use actually all toolboxes. Just the laser resonator toolbox is not required. I will give you in the following an introduction into homogenization and shaping concepts for LED light. So this is just an overview, and at the end of this overview I will explain which concepts or which DOE types require which toolboxes of VirtualLab. And after this introduction of the shaping concept, I will show you samples so that you just get a feeling how the homogenization of LED light works in VirtualLab. So actually the homogenization concept that I will show in the following will not work only for LED light. We can be used also comparable for Excimer laser light. So the light models and the light properties of Excimer laser and LED lights are quite comparable. And for LED and Excimer laser light, we can use the following concepts. We can use microlens arrays for homogenization. We can use diffractive diffuser elements, and diffractive diffusers are sometimes also called kinoforms or computer-generated holograms or faceplates. And we are able to use arrays of cell arrays of gratings, prisms, and mirrors. So we call this grating cell arrays, prism cell arrays, mirror cell arrays. Let's start with microlens arrays. If we use microlens arrays for the homogenization, then we have an optical setup with typically a collimation lens and often also a field lens or Fourier lens here that generates in the focal plane the desired homogeneous light distribution. And in between we have a single lens array, or maybe also in some cases 2 or 3 lens arrays, depending on the optical setup that we like to use. And this lens array are actually required or responsible for the generation of this homogeneous light distribution. Especially if we use here refractive lens arrays, as you can see it here on the right, we are able to shape monochromatic and white light LED, because these refractive microlens arrays are not so sensitive for wavelength changes. The shape of the light distribution that we can generate actually depends on the lens aperture and the lens shape. So typically just circular, rectangular or hexagonal shaped light distributions are generated. But I just like to mention that it's in principle also possible to use some freeform lens surfaces or aperiodic lens arrays or randomized lens arrays that generate more general 2D light patterns. But as also the sample that I will show in a little bit later is just for some rectangular patterns, so that are the most typical applications. What you see here, this is a typical one-dimensional profile of a light distribution generated by a microlens array. I like to mention that the field tracing simulation in Virtual Lab always includes diffraction, interference, and degree of coherence. And we can see here, for example, in this light distribution that we have some remaining interference shrinks that just indicate that the homogenization is not perfect. And we are able, or you are able as a user of Virtual Lab, to predict very accurate what are diffraction efficiencies and what are uniformity errors in different parts of an homogeneous light distribution. So what's now the difference of a diffractive diffuser element for homogenization? Diffractive diffusers or setups with optical setups with diffractive diffusers consist of a so-called beam optics, or we like to call it beam optics. That means beam optics, this can be in collimation lens, it can be in focusing lens, and beam expander, or an imaging setup. And the beam optics is just responsible for generating a very narrow spot in the target plane. And this spot determines our optical resolution that we have. And if we add now a diffractive diffuser element, this element generates a lot of diffraction orders. All diffraction orders have almost the same spot size. And this diffraction order should be as close as possible so that we overlap. And if all spots are incoherent or let's say have just a very low degree of coherence to each other, then we get a homogeneous, speckle-free light distribution. I like to show this on one practical example. Okay, first of all, this is one of the examples that I like to show. You have here an 8-level diffractive diffuser element, and on the left side, for example, in homogeneous top-hat distribution. But let's take a practical example from our lab. This is a diffractive diffuser element illuminated by a collimated single-mode laser beam. And we get here on the target plane the skyline of the city Jena. And as I mentioned, a diffractive diffuser generates a lot of diffraction orders that are very close to each other. And if we have coherent single-mode laser light, we get speckles in the target plane because of the interference between the diffraction orders. But if we illuminate the same diffractive diffuser by an LED, so this is done here by collimated LED light, then we get in the target plane a very homogeneous light pattern. And you can actually also see that we are able to generate very general light distributions by diffractive diffusers. So what you see here, this is in part of this 4-level diffuser structure used for the generation of this skyline. So diffractive diffusers can be used for the generation of almost arbitrary 2D light distributions. I just like to mention again that diffractive diffusers are also often known as computer-generated holograms, faceplates, or kinophones. Diffractive diffusers are wavelength sensitive, so they are just good for monochromatic LED light. If you like to generate polychromatic light distributions, it is recommended to use red, green, and blue LEDs and to design 3 DOEs for every LED so that you have the best diffraction efficiency and the best quality. But we have also to take into account that for high NA applications, so that means if you need diffusers with very huge diffraction angles, that analysis and design of these diffusers can be actually also slow and probably not so accurate. And because of this, Leitfans developed another approach, and we call this cells arrays. So the idea is here that we can decompose our diffractive optical element in small rectangular cells. And every cell creates, just by diffraction at the cell aperture, a small spot in the target plane. And if we have several cells, then we can generate a lot of spots in the target plane, and we can generate a 2D light pattern. The spot size in the target plane actually depends here on the distance between DOE and target plane. It depends very strong on the cell diameter. So by using smaller or larger cell, we can control easily the spot size and the optical resolution in the target plane. And actually the spot size in the target plane depends also on the size of our LED chip that we use and on the distance between LED and DOE. So the light deflection within a cell can be done by different structures. We can use a grating, for example, a rectangular grating or placed grating, and in this case we call this grating cells array. Or we can use a small microprism or micro mirror for light deflection, and then we call this prism cell or mirror cells array. As I mentioned, we can generate here 2D light patterns in the target plane, and especially prism cells and mirror cells arrays can be used for white light as well as monochromatic light. Grating cells arrays are quite wavelength sensitive and are just good for monochromatic light. Let's see a practical example. This is here a grating cell array, and actually there are two grating cell arrays, and we illuminate now this right here on the right side. This grating cell array is by green LED light, and this grating cell array shapes a cross pattern that is very homogeneous. In addition, I illuminated this grating cell array also a little bit by white light, and every colored spot that you see here in this grating cell array corresponds to the reflection of a single grating cell. So these grating cells can be quite large, so maybe in the range of several tens or 100s or hundreds of microns. So you can see this just with your eye. Then if I illuminate with white LED light through this grating cell array, then you see here on the left side that we get actually a very colored light distribution. We have relative strong chromatic effects. We get color effects that actually are unwanted. And the reason for this color effects is that we use diffraction for the light deflection. And gratings, small gratings for light deflection are quite wavelength sensitive. And because of this, Leitfans developed so-called prisms or mirror cells arrays. And here you see an CAD drawing of this of a prism cell array surface. And prism cells and mirror cells are less wavelength sensitive. And this is shown on this example. So we designed here for green light 532 nanometer grating cell array, prism cell array, and mirror cell array. And if you illuminate the grating cell array with white light, then you see that you actually get just a very good green light trans logo, but for blue light and red light we have just noises. So this grating cell array here in this case does not work for wavelengths that are far away from green light. If you use instead a prism cell array, then you see that we get a nice white logo of light trans. But if we magnify a small region of this logo, then you see a little bit here red color and blue color along here these lines, along these borders. That are some small chromatic effects that come from the wavelength dependence of refraction that is used for in this prism cell arrays for light deflection. Mirror cells arrays use reflection for light deflection, and here these chromatic effects completely disappear, so we can get very nice achromatic light distributions. Okay, there's one question. The question comes from Mr. Sagiri, and he asks, how accurate should be the wavelengths of LED specified as an input for the modeling? So the design is typically done for a single wavelength, but for the analysis of the resulting cells arrays, actually an accurate power spectrum should be used. That means you should use at least, let's say, in Gaussian power spectrums. The most of the monochromatic LEDs have an more or less Gaussian power spectrum with and you should use for the simulation the correct bandwidth, but it is actually better to import a power spectrum. So if you get some data, for example, in an ASCII file or in an Excel file, then it is possible to import this power spectrum data into Virtual Lab. Okay, and I will show you later a little bit on an example how many wavelengths you should really use for the simulation. So let's skip this for one moment. So which toolboxes are actually required for the simulation of these different optical setups? With the starter toolbox, you are able to model LED and Excimer laser light, and it is possible to simulate lens system, including, for example, diffractive optical elements or microlens arrays, or computer-generated holograms or diffractive lenses, and so on. In addition, the starter toolbox enables also the optimization of microlens arrays, so you have a parametric optimization, and you can optimize the lens shape, for example, to get an specific light distribution. The diffractive optics toolbox is good for the optimization of diffractive diffuser elements. As I mentioned, the starter toolbox can analyze homogenization systems with diffractive diffusers, but if you want to optimize the diffractive diffusers, you need the diffractive optics toolbox. The design and simulation of grating cell arrays, prism cell arrays, and narrow cells arrays is included in the lighting toolbox. And if you design and especially analyze grating cells arrays, it is recommended to have the grating toolbox in addition to the lighting toolbox, because it can happen very fast that you have gratings with periods in the range of the wavelengths of light. And if you have so small gratings, you need typically an exact, rigorous electromagnetic simulation of the grating efficiency to predict very accurate the light distribution in the target plane. And the grating toolbox can be used to create a lookup table with diffraction efficiencies of the different grating cells, and this lookup table can be used in the lighting toolbox. And this is actually also the strength of this grating cells arrays concept. For example, compared to diffractive diffusers, we are able to calculate the diffraction efficiency of the grating cells, very accurate, also if we have grating cells in the range of the wavelengths of light. Before I start with some samples, I like to say some words concerning the modeling of partially coherent light. You know probably from optics books that partially coherent light can be represented or described by coherence functions, but we are using here a different approach that is, let's say, more simple to handle in computer simulations. And we describe partially coherent light by sets of harmonic fields. A harmonic field is a coherent monochromatic field. So with one harmonic field, we can model a single mode laser beam. But if we use a set of harmonic fields, we are able to model, for example, color distribution, stationary sources in color. We can simulate temporally partially coherent light. We can model spatially partially coherent sources as, for example, multimode lasers, Excimer lasers, VCSELs, and especially LED light. And I'd just like to mention we are also able to model non-stationary sources and especially ultra-short laser pulses. So that means if we have an LED source, we need to describe the partial coherent light distribution of the LED by a set of harmonic fields, or we can call actually these harmonic fields also modes. And for LED modeling, we use so-called quasi-homogeneous partial coherent sources. And the idea is here that we assume that all modes start in a plane. This is typically the LED chip plane. And we assume that all modes have the same shape. The shape of the modes actually depends on the far field intensity of the LED. That means if you have, for example, a measurement of the radiant intensity of an LED, then it is possible to calculate from the radiant intensity of the LED the mode shape. And in addition, every mode can have a weight, and this weight depends on the power spectrum and also on the near field intensity. That means we can measure the near field intensity of an LED, and so you see typically some wire structures that are on top of the LED chip, and Virtual Lab can calculate from this near field intensity the weights of the modes, and every mode will get, depending on the source point, a different weight. I'd just like to mention that for different partial coherent sources, different from LEDs, probably different models are required for the modeling of good and correct modeling of the light distribution. But this quasi-homogeneous partial coherent source model is good for LED light. So let's start with one example, and this is the simulation of the homogenization system with a lens array. So let's consider the following setup. It's a so-called imaging lens array homogenizer. That means we have here a light source, an LED source, we have a collimation lens, and now we have typically two lens arrays. And behind the lens array is a Fourier or field lens. And the idea is, or the name imaging lens array homogenizer comes from the working principle. This Fourier lens here images the aperture of the lens, of the single lenses in the lens array into the target plane. So every lens aperture is imaged in the target plane, but all images of these different lenses of the lens array are at the same position, and so we get a homogenization effect. In this example, let's assume that we have a collimation lens with 20 millimeter focal length. The Fourier lens has 100 millimeter focal length, and the lens arrays, these two lens arrays have a focal length of 0.903 millimeters, and the lens pitch or period of the lens array is 200 microns. I like to mention that it is very important for lens arrays to include in the simulation partial coherence and diffraction effects, because we get here at the apertures of the first lenses here, of the first lens array, diffraction effects. What we actually get here in the plane of the second lens array, this is something like the point spread functions of all lenses of the first lens array. And these point spread functions are cut by the apertures of the second lens array lenses. And because of this cutting process of the point spread function, we get some diffraction effects, some filter effects that can lead to some serious distortions, intensity distortions and modulations in the image plane. So let's switch to Virtual Lab, and I like to show you here on this in Virtual Lab this example how the simulation works and how the homogenization works. So we have here an LED source. I use a so-called Gaussian type planar source. It means that all modes start in a plane and that we assume that the modes have a Gaussian shape. So this is just a rough approximation of an LED. I just like to mention that it is also possible to import measurement data into Virtual Lab to have a more realistic LED model. So we have here an idle collimation lens. This is the first lens array. It consists of the array and an additional lens array aperture. This is the second lens array, and this is the Fourier lens. The simulation of the lens array is actually quite simple. This is here an idealized lens array model. This is for an initial design step sufficient, but it's actually also possible to model and lens array by real surface profiles. And here in this idle lens model, we have a periodic mode. We just enter the period or the lens pitch, and we can enter the effective focal length. And in the Gaussian type planar source that we use for the LED modeling, we can enter here a power spectrum. Actually here a Gaussian power spectrum is used. You can import this power spectrum from an ASCII file, or you can actually also use some generator function that we have in Virtual Lab to get, for example, a Gaussian power spectrum or constant power spectrum or black body spectrum and so on. And in this source, and this makes actually this Gaussian type source simple to handle, we just need to enter the source plane diameter in XY direction, and we can enter the divergence angle. And to reduce here for this webinar the simulation time, I reduced the divergence angle to 5 degrees, but it's not required. Also important is that I will use here in the following and one-dimensional simulation, because I use here rectangular lens areas or rectangular lens apertures in the lens array. And if we have rectangular lenses, we get actually also a rectangular light pattern in the target plane. And so there is no need to make a full 2D simulation. We can save a lot of computational time by running two one-dimensional simulations, one in X direction and another one in Y direction. And this is what I want to do in the following. So, and the next important point is, I mentioned that we model partial coherent light in Virtual Lab by sets of modes. And the question is, how many modes should be used? And this can be controlled on the mode selection page of a light source, of a partial coherent light source. We have here actually in the upper part of the dialog an option to control the lateral modes that are responsible for the modeling of the partial coherence, of the spatial partial coherence. And for a good result, we need here 480 lateral modes. And in the lower part of the mode selection page, sorry here, especially in this region, we can control the number of wavelengths that we use. And wavelengths are actually also related, or the power spectrum and the number of wavelengths that we use are related also to the temporal coherence simulation. So in the following, I will use just one wavelength, and I will restrict the lateral modes to 9 modes, just to show you in the beginning the effect of the homogenization, or the homogenization effect of the lens array. So let's run the simulation. So on what we get is the following. What you see here, this is the light pattern generated by a single mode. So a lens array is a periodic structure like in Grating, and if you have a periodic structure, we get a lot of peaks of discrete diffraction orders in the target plane, and this is what you see here. So for one source point of the LED, we get actually something like a grid pattern. So, and if we now can see the light pattern generated by another source point, then you see that there is again a grid pattern in target plane, but these grid patterns are shifted to each other. And this is actually also the homogenization concept of these lens arrays. We generate a lot of discrete periodic patterns, but for every source point of the LED, a shifted pattern will appear. And if we adjust the lens array parameters like pitch and focal length exactly to the dimension of our LED chip, then we will get a very homogeneous light pattern. And I will show this just here on on one slide. So if you use 480 lateral modes and 24 wavelengths, and calculation needs around 1 or 2 hours, then we get and light pattern and one-dimensional light pattern in x direction like this, we see we have still some remaining ripples here, but this is caused by diffraction effects, and if you like to overcome these effects, if you like to have a more homogeneous light pattern, then we have to optimize creating lens array pitch, focal length. We can change the focal length of the collimation lens, and we can probably select a different LED with a different chip size. Okay, now let's come to the next example, and this is the homogenization of, in this case, Excimer laser beam by a diffractive diffuser element. I like to mention that you can do the same homogenization by, for LED light, but I just like to show you that actually the same concept will work also for any Excimer laser beam. So let's consider the following setup. We have an Excimer laser, we have a collimation lens with 20 millimeters effective focal length, and now we have a diffractive diffuser. And for simplicity, I will just simulate this diffractive diffuser in this plane by a phase function, by a phase plate. Yeah. And the goal is to generate a circular top hat in a distance of around 500 millimeter from the diffractive diffuser. The Excimer laser has a source plane diameter of 100 by 100 microns. The divergence angle is around 0.9 degrees, and this corresponds to a spatial coherence length of 3 by 3 microns. The diffractive diffuser is optimized, or was optimized by Virtual Lab. It's an 8-level diffuser with 5 micron pixel size. Let's assume that we know already this diffuser, and let's just consider here in this sample the analysis of the setup. I will show you later how you can design a diffuser like this. So I will change to Virtual Lab. So this is the light path diagram with the optical setup. I will use again this Gaussian type planar source for the Excimer laser modeling. And here this so-called stored function, it contains the phase function of the diffractive diffuser element, and it looks like this. And if I zoom in, then you can clearly see that we have 8 different discrete phase levels. So I will run the simulation. It takes a little bit of time because I will use now, I will run now a 2D simulation with 11 by 11 modes. So we have 121 two-dimensional harmonic fields that must be propagated through the optical system. This takes a little bit more time, but I like to point out the concept here is so simple to handle for partial coherent light because of the decomposition of the partial coherent light in harmonic fields. Because if we can handle the propagation of a single harmonic field, if we can analyze a system for a single mode laser beam, then it is very simple to simulate the same system for partially coherent light, because all propagation models, all propagation concepts that we know for single mode laser light can be actually also used for multi-mode laser light, can be used for LEDs, for Excimer lasers. So the simulation was done. What you see here actually in the light view of Virtual Lab, this is the intensity distribution in the target plane. So Virtual Lab superimposes the intensity of all modes, of all 121 modes in the target plane, and the resulting intensity distribution can be used to evaluate or to check the homogeneity and also the diffraction efficiency of this diffractive diffuser. And you see, this is already quite homogeneous. There are some remaining interference patterns here or noises. This can be reduced or future reduced by redesigning the diffractive diffuser. Actually here in the detector result window, here in the lower part of Virtual Lab, you see that we have a diffraction efficiency of 88%, and the uniformity error is around 12%. So now let's see what is the output for the different modes. And this can be seen if we switch here to the data view of Virtual Lab. You see, for one single source point, for one mode of the light source, we get actually here a speckle pattern in the target plane. And if I switch from mode to mode, then you see that the different speckle patterns of the different modes are shifted to each other. And this is how the homogenization actually works in this case. We have an almost constant speckle pattern, but for every source point of the light source, a shifted pattern will appear. And since we since these different modes are incoherent to each other, we get a nice homogenization effect. So now let's see how we can optimize a diffractive diffuser as used in this example. And a typical optimization algorithm that is typically used is the iterative Fourier transform algorithm. I'd just like to give you some information about this optimization algorithm. DOE optimization can be done, for example, by this iterative Fourier transform algorithm, but sometimes also parametric optimization is used. But I like to point out that typical diffractive diffuser element, as we used here in the previous example, have 10,000 or probably also 100,000 or millions of free parameters. And the IFTA algorithm is a very efficient optimization algorithm to optimize these DOEs. What are the difference between parametric optimization and IFTA algorithm? If you run a parametric optimization, you need to define a merit function, and this merit function is optimized by a specific local or global optimization approach. That means any light distribution that you like to get needs to be translated into a merit function. And this merit function is optimized. Instead, the IFTA algorithm optimizes a target intensity distribution. So that means actually you define a desired light distribution in the target plane, and the IFTA tries to find a DOE that generates this target intensity distribution. So there's no need to define merit functions. The IFTA algorithm is typically done in two steps. The first step is a so-called transmission design. It means we optimize the optical function of an optical element of a DOE, and we take already into account some constraints during the fabrication process, for example, discrete pixels or discrete height levels that we can fabricate. And the second step is the calculation of a height profile or of a refractive index distribution from this transmission function. This IFTA algorithm has the following working principle. Let's assume we have an initial guess for the transmission function of the DOE, and now we analyze the optical system we propagate into the target plane. So we get typically an intensity distribution that is different from what we want to have. And now this IFTA algorithm corrects the intensity distribution. So just in some parts in the target plane, the intensity is corrected. And now we get a new light distribution, a new harmonic field in the target plane, and this is propagated backward to a plane behind the transmission function. And now we can calculate a new transmission function of the DOE, and we have again to take into account some fabrication constraints, as for example, if you have a discrete height level element, or if you need to fabricate a discrete height level element, then you can just generate discrete phase levels. And because of the introduction of these transmission constraints, we introduce again some stray light in the target plane, and so we have to run maybe several hundreds or thousands of iteration loops to find a solution and transmission function that can generate it, for example, by a height profile that we are actually able to fabricate, and in addition, this resulting transmission function creates also a very good intensity distribution that we need. So let's come to one example, and this is the design of a diffractive diffuser element for a rectangular top hat-like illumination. So let's consider the following optical setup. We have a collimated laser beam, red laser beam. The goal is to optimize a diffractive diffuser element with 2 height levels or phase levels in case of a transmission function and a pixel size larger than 1 microns. And the goal is to generate an angular, rectangular top-hat distribution. So it's an angular distribution with a top-hat shape. So the light source has a wavelength of 632 nanometers, and this desired output pattern should have an angular diameter of 1 degree and a resolution of around 0.03 degrees. So let's again switch to Virtual Lab. Yeah, for the design of such diffuser elements, we have some built-in wizards, and these wizards are called session editors. If you like to start with a new wizard, you can click on Design, Diffuser Design, and select Regular Shape Diffuser or Pattern Generating Diffuser. I will use here actually in the following the Regular Shape Diffuser editor. It is good, the session editor, for the generation of top hats and lines. Actually, this pattern generating diffuser session editor can be used for the generation of arbitrary 2D light patterns. You can import, for example, in bitmap or an ASCII file with the desired light pattern. So this is the regular shape diffuser session editor, and you can enter here the laser beam parameters. We will run actually in the beginning the full optimization for a single mode laser beam, and in the next step we can use it for a multi-mode, for example, LED laser beam, laser source. So we can select here the optical setup. We have different typical setups, angular setup, Fourier setups with a Fourier lens, far field setups. So here we can select between top hat and line, and if we select top hat, we can select between elliptical and rectangular shape. On the next page, we enter the top hat diameter and the angular resolution. That means the smallest features that we want to resolve. And you need to take into account that a DOE does not diffract all light in the desired light pattern. So we have always some losses, and these losses, this is stray light. It is diffracted to higher diffraction angles. And if you need to reduce the maximum intensity of this stray light, then you can introduce this limit intensity of stray light feature. So here the intensity, the maximum intensity of this stray light is limited to 15% of the top hat intensity. So we can enter here on this side the number of discrete levels of phase levels that we want to design. That means we will get a 2-level element here that can be, or these 2 phase levels can be generated, for example, by 2 different height levels. So, and now Virtual Lab calculates automatically the required pixel size of the DOE and the period. And if you click on Finish, Virtual Lab generates a light path diagram with the optical setup and an optimization document. This light path diagram is not optimized at this point. That means it just generates in a single spot, but no top hat pattern. We can start here the optimization of this DOE by the iterative Fourier transform algorithm, and after the end of the optimization, the resulting DOE is automatically included or added to this light path diagram. So you see it can take a little bit time. It requires here around 1,100 iterations to get a result. To analyze the output, to get some merit function results, we can already switch to the analysis page here of the optimization document and click the recalculate button. So what we see here is that the efficiency is around 73%. And what we get here on the left side in the data view, this is actually that are the diffraction orders generated by the diffractive diffuser. So that is not the light pattern in the target plane, that are diffraction orders. So every pixel corresponds to the diffraction, to a different diffraction order. So what you see here, this is, for example, now the intensity of the diffraction orders. If you like to see the light pattern in the target plane or here in the angular domain for a coherent single mode laser beam, you can use the light path diagram, and you see here clearly a speckle pattern, and actually here in the light view the speckle pattern would look like this. If you like now to see what's the output, what's the light distribution for an LED source, then you can just easily replace this single mode laser beam by an LED source. So let's skip these slides because I showed this. I just like to say some words concerning fabrication expert. Okay, there's one question. Okay, Harry Skolnick asked, how can I design a reflective DOE to produce a custom shape such as a company logo? Yeah, this is actually so far comparable to what I showed, because at this point we have not a real surface profile. This is just a transmission function and phase function, and this phase function can be the phase function of a transmittive but also of a reflective DOE. So what we still need to have some fabrication data are two different steps. First of all, we need to calculate a surface profile. And for the calculation of the surface profile, typically the so-called thin element approximation is used. That means we assume that the height profile is proportional to the calculated phase function. And for transparent plates, we use this equation to calculate the height profile, and if you have a mirror, a microstructured mirror, we use this equation for the calculation of the height profile. I like to mention that this equations, or that this thin element approximation is valid for DOEs with features or with pixels larger than approximately 5 times the wavelength. So if you have significant smaller pixels or features, you should take into account that this model for the height profile calculation is not exactly or not correct. There can be some deviations between, let's say, experimental results and simulations. These deviations are probably not so critical if you like to generate just a logo, if it is in visual applications. But let's assume if you like to have an DOE, for example, for material processing, and you need to have a very high accuracy of the intensity distribution, then these deviations can be already serious if you are, let's say, if you have features in a range of 5 wavelengths. So, and the next step that you need is you need to export the surface profile that you calculated by into the correct file formats. Let's take the diffuser that I optimized here. So if you like to have a surface profile from this diffuser, you can click on Design, Structure Design. You can select between transparent plate or mirror. You have to select or to define the substrate material. I will use a few silica. You have to specify again the design wavelengths. And here on the last page, you need to specify the number of height levels again. So I will select here 2 height levels. And Virtual Lab calculates automatically the corresponding modulation depth. This is here 507 TV7 nanometers. And if you click OK, you will get a new light path diagram with the microstructured component. So component looks like this. It's actually looks like a plate, and this is actually normal because the modulation of the surface profile is very, very, very small compared to the diameter. I will scale a little bit the surface profile, and now you can see here on my computer screen a 3D image of this surface. But please take into account that here, depending on the structure resolution and depending on your graphics card, maybe the optical resolution that for your computer screen is a little bit restricted. But I think you can clearly see here the different microstructures. So, and if you like to export this, you can click on this Tools button, select Export, And now you have the option to export to different ASCII or text file formats. You can generate or calculate etching mask. If you have a multi-level element, you can generate GDSII and CIF or bitmap files, and especially CIF, GDSII and bitmap file format are often used for the etching process, and especially GDSII and CIF files. These are vector data files that comes from microelectronics, and they are typically also used for micro-optics. So Virtual Lab can calculate, in case of multi-level elements, a different etching mask, and can export this etching mask in different file formats. So we have another question of Rand Dunmerk. He's asking, how about mirrors operating at an angle of 45 degrees? If you have a mirror that is tilted to the optical axis, the design can be a little bit more complicated, especially this design step that requires the calculation of the height profile can be more complicated. So the structure design that I showed here was assuming a mirror that is perpendicular to the optical axis. If you have a strong tilt, then I just like to mention that we have a design sample on our web page that explain, for example, for a beam shaping element, how you have to run the design, which design steps you need to do to get for the transmission function as in corresponding height profile. So I think, Mr. Dunnerberg, I can send you this sample so that you can go through all design steps. So now let's come to the final sample that I like to show you. This is the design of an grating cell array for the generation of an cross pattern. So let's consider the following optical setup. We have an LED here, 5 millimeters. In front of the LED is a grating cell array. The substrate thickness is 2.5 millimeters, and the goal is to generate in 100 millimeter distance at a target plane and cross pattern that looks like this. So this pattern is specified by a bitmap, so you can use, for example, in painting software to generate an arbitrary light distribution. You can actually also use a text file to specify an intensity distribution. And here this light pattern should have a diameter of 30 millimeters. The grating cell array used for the light shaping should consist of 100 by 100 cells with 100 microns cell size. So the grating cell array has 10 millimeters by 10 millimeters diameter. So let's again switch to Virtual Lab. So I will close here all windows. So if you like to start with a setup of a grating cell array light path diagram, you need to click on Solutions, Lighting Toolbox, because grating cell arrays are included in the Lighting Toolbox, and you can select your light shaping system with grating cell array. And then you will get a light path diagram like this. Only difference is that this light path diagram that I loaded here in Virtual Lab contains already all settings that I need. So we have a camera detector, we have the light shaper, this is a glass plate with the grating cell array, and we have a so-called far-field source for the LED modeling. And the far-field source is very good if you have measurement data of an LED. So if you have a far-field measurement and near-field measurement, then we can import this into the far-field source and use it for the modeling of the LED. The light shaper has, in this case, it's a transparent plate, and so it has on the second surface a grating cell array element. And you see here that we have 100 by 100 cells with 100 microns cell size. It's shown here. And this table contains, for the different grating cells, period and rotation angle and an additional grating shift. So, if you like to design this or calculate these grating parameters to get the correct shape, the light distribution, you need to click on Design and select New Cells Array Design. So this is a very specific design algorithm that helps you to calculate the different grating parameters. So you need to select the design wavelengths, and you need to specify a reference field. So what the field or light distribution, intensity distribution that you like to get. So click here on that, and you can, for example, import this intensity distribution by from a bitmap or text file. So we have here an import wizard that assists you during the importing process. You need to select the light distribution. Actually, light distribution here is this cross pattern. There is a dialog that asks you for the color palette that you used in the bitmap. This is very important because we have to convert the color palette into intensity values. So we recommend actually to use a grayscale color palette, and here the intensity value 0 corresponds to black color, and intensity value 1 corresponds to white color. Okay, we need to select in this table what is the physical unit of these different gray values, and I will select here electrical field strength squared. That means it corresponds to an intensity. On the next page, we have to tell Virtual Lab that the x and y axis have the units length, and we have to set the length of the x and the y axis, and it is actually 30 by 30 millimeters. That means the pattern of the bitmap has 30 by 30 millimeter length. Now we can click Finish. If you like to show the imported light pattern, you can click here to Show Pattern, and you see it's across. So that is the most important step. We have some other features here in the dialog. Variability of spot positions means that you can introduce a random shift and random error of the different spots in the target plane. This is sometimes good if you cannot set or if you cannot use a sufficient large number of spots in the target plane, and you get sometimes some regular patterns that really disturbs an application. But with this random spot shift, you get such some random intensity noises that is typically not so disturbing for several applications. I will introduce here 25% error or random position error. 25% is related to the diffraction order distance in the target plane. And this use fabrication constraints is often also of interest. You can limit the smallest periods of the gratings, but please take into account that from a physical point of view, and depending on your distances on your light pattern, you need a minimum period to deflect the light to the target plane. But if you are, let's say, close to your fabrication limits, you can introduce this minimum grating period, and then Virtual Lab will not use periods smaller than this value. But please take into account that depending on your optical setup, maybe the generation of your light pattern is not possible or will not have the best quality. So if you have this, just click the Go button and you get a new light path diagram. And you see this is very, very fast because we don't use here a parametric optimization. We have just an analytical algorithm that calculates just by the grating equation for every spot in the target plane the corresponding grating parameters. So I will show you in the following the output light distribution. I need to change here a little bit the parameters. I will start actually with a ray tracing simulation, and I will use in the beginning around, let's say 100 by 100 rays, and I will select here ray tracing. And then ray tracing simulation is possible here because we have we can use the grating equation to calculate the deflection of the rays at the grating cells. And you already see that we get here more or less a cross pattern. If I switch to the 2D view, we can see the dot diagram. You see that this is a cross. But what we cannot see by ray tracing, this is the exact intensity shape, because we have some diffraction effects at the grating cells, and we should use a field tracing simulation to get an exact light distribution. So let's switch to field tracing. Let's use for the simulation 3x3 lateral modes, and here just in single wavelengths. So it takes now a short moment, but you see that we are actually again very fast, and that we get now a light distribution including diffraction effects at the grating cells. So let's imagine if you have an illumination ray tracing software and you like to get a homogeneous light distribution like this, you have to use maybe hundreds, thousands or millions of rays, and this takes, I think, a significant longer time. Here we have just, the simulation requires actually just 7 seconds, but we got already in second sevens an accurate prediction of the light distribution, including diffraction and partial coherence. So I like to mention that if you like to have a more accurate simulation of the light pattern, then you need probably to use in the background the grating toolbox. For this simulation, I assume that the diffraction efficiency of the gratings, of all gratings, is constant, independent on wavelengths and incident angle. But we know if you have very small gratings in the range of the wavelengths of light, that probably the diffraction efficiency can change depending on the grating period. And to model this, we have the so-called local linear grating analyzer that we can select. And this analyzer creates a lookup table with the help of the grating toolbox. So you just enter the number of height levels of your gratings, for example 2 levels. You need to enter the modulation depth of the gratings, and the grating toolbox is used to calculate the diffraction efficiencies of the gratings depending on wavelengths, incident angle, and period. This can take a little bit longer time, also several hours. But if you have the lookup table, you can specify it here in the light shaper, and the lookup table is used for the field tracing simulation, and the field tracing simulation is again very fast. So this was the last sample. I just like to say some words concerning fabrication data export for grating cells arrays. In the grating cell array dialog, you have here in the lower left corner again an export button, and if you click this button you get this dialog, and in this dialog you can again calculate etching mask, and you can export the data in an ASCII or text file format, or you can select GDSII data, and I think GDSII data is typically recommended for fabrication of the grating cells by etching. So I like to summarize this webinar. Virtual Lab enables design and analysis of micro-optical components for shaping and homogenization of LED light, and I showed you especially homogenization and shaping of LED light by microlens arrays, diffractive diffusers, and arrays of grating, prisms, and mirror cells. The full simulation of the optical setups of this with these micro-optical elements is done by field tracing, by unified field tracing, and this includes diffraction, interference, and partial coherence effects. And I showed you that you can export the surface profiles in different data formats, and especially for etching of DOEs of microstructured surfaces, GDSII files, ZIP files, ASCII and bitmap files are of importance. So there's another question of Van Dannenberg. Yeah, he is asking for the YouTube link. Yeah, I think as soon as we uploaded the slides and also the video to our webpage and also to our YouTube channel, we will send all participants an email. So there are also some participants who registered for this webinar, but did not find time to take part. And so we will send on all a newsletter with a link. But if you like, you can actually also check our YouTube channel. Just go to YouTube, enter Light Trends, and then you will find our YouTube channel, and you will actually find also other webinar videos from different webinars, and also videos from solutions and from application scenarios. I like to mention again, if you like to learn how to run and design, and if you like to have more background knowledge of the physics required and also of the optics required for the design of these microstructured elements, then I recommend to join or to register for our software training end of March next year. It is focused on the design and simulation of micro-optical elements for homogenization and shaping of partial coherent light. And sure, if you like, we always offer also customized trainings at your locations if you don't like to wait till end of March. If you need a trial version of Virtual Lab, and if you are new and start to work with Virtual Lab, please go to our webpage www.lighttrans.com and go to the download area of our webpage and register for a trial version, and we will send you the trial version. Okay, thank you very much for your time, and thank you very much for attending the web.